Today we'll be solving some nice limits. We'll start with number 2. So the limit of n as it approaches n to the 4th minus 2 of n. If you evaluate this just normally, the inside and outside, we see that's 1 to infinity, which usually means it's a Euler identity problem. So I'm going to rewrite it as n to the 4th minus 2 of n plus root n squared plus 1 minus root n squared plus 1 all over n to the 4th. Okay, you already know what this is, right? We can take out the 1, so the 1 would take this term as well as this term, so it would be left with these two. So negative 2 of n minus n squared plus 1 all over n to the 4th plus n squared plus 1. Of course, to the 2n cubed plus 5. We want it to be in the form 1 plus 1 all over x, right? So we'll flip this to the bottom. So it'll just be 1 plus 1 all over n to the 4th plus and we want to have the x there, so we'll put this on the top as a power. And we can't just do that for free, so we gotta do the reciprocal. Well, not the reciprocal, but the inverse. And then we have our 2n cubed there. Now we know that this at infinity evaluates to e. So now we're going to evaluate this thing. So we could ignore this part because it won't be a highest power. So at infinity it'll kind of become irrelevant. And then we have these two terms. This one's kind of important because this will be an n, and this will also be an n, and it will be multiplied by n cubed, which will give us a similar degree power, and then we'll use the rule of coefficients. So we'll do negative 2 and minus we'll take out the n, so this would be then 1 plus 1 all over n squared all over n to the 4th plus, we'll write it in. Right. Now we distribute this. This would become negative 4 n to the 4th, and also this will go to 1, so we could ignore that and just consider this a negative 3n, and then do this. So then this would be negative 6 to the n to the 4th plus negative 15n all over n to the 4th plus this other term. You know this rule of coefficients, right? And this will be the exponent. So this is the solution to number 2. Next we got limit as x approaches 0. So I believe this is another Euler identity that approaches 0. In the case where it approaches 0, this is equal to e. so we'll start off like that. 1 plus x. We'll multiply by the inverse. Another inverse. And then 1 all over x natural log. Now we observe one thing. If we combine these, this thing looks kind of familiar. Sine of x over x, and there's a way to convert this natural log to something nice. So we'll take advantage of the identity that as this approaches 0 is 1, right? So we'll divide by negative 2x and also multiply by it. Then we see that this goes to e. This would be 1, this would be 1. So what are we left with? We're left with x all over negative 2x. These cancel out, and we're just left with e to the negative half, which is equal to 1 all over root of e. Let's erase this. So now we're working on number 3. So the first step is to figure out how we approach this. When we first write the problem, we observe that this first term is in an indeterminate form, and so is the second. So we're going to separate this, so we'll use the rule of separation of limits. And we L'Hopital's this. X plus x. 1 plus 3x cubed. Now this approaches 2. We have minus this limit of 1. This approach is, we don't know, it's undeterminate form. So we'll consider this a limit as well, which is still just 2. Then we combine these. Cross multiply. And then we see this is undeterminate. So we do L'Hopital's again. We get to cosine of x. This becomes 0 all over cosine of x. Now the limit as approaches 0, obviously, if this is 2. We can cancel it out. Now we'll work on this little limit. So this is a squeeze theorem problem, all 3 of these. And the first part of this is, what do we observe? So we got 1 over n squared plus 1, and all of these are multiplied by n. And the bottom goes like this. So what if we put n squared plus 1? Wouldn't this be the largest series? So n times 1 all over n squared plus 1. And this, obviously n times, which we don't have to write, it would be the same as the sum of n all over n squared plus 1, right? So this would be the infinite sum of the m's times n squared plus 1. Now, if we assume that there is no 1, 2, or 3, but this is always n, so these numbers, the sum will be always smaller, we'll do the same thing. N times n plus 1 all over 2 times n squared plus n. And this will always be smaller. Let's simplify this. Over here, this would be n squared plus n all over 2n squared plus 2n. And likewise on the other side. And by the coefficient rule, this converges to 1/2, and this one converges to 1/2. So now we know that this converges here. Okay, next we're gonna do this. Now let's just observe the inside part. So nth root of the inside part, and 2 times 3 of n plus 4 times 7 of n. What's a case where all of this would be larger? So let's assume that instead of 3 of n, we have 7 of n. This would be 2 times 7 of n plus 4, so this would be 6 times 7 of n. Also a case where it will always be smaller. Now we can just say 4 times 7, or even simpler, let's just do 7 of n. And now we put the nth root on it. Another nth root of this. And then we see that this is 7 to the n times 1 to the n. And this is 6 to the 1 over n times 7 to the n over 1 over n. Right, then we see as these cancel out. This is just 7. This goes to 1, this goes to 0, so this goes to 1. This is 7. And this is 7. So the limit is 7 in this case. Let's get another example. In this case we have an alternating digit, -1. And well, this looks like a Euler form because the n squared over n squared, that would take us to a 1, and then this would be to infinity. So we would do n squared plus, the smaller case would be -1, right? All over n squared plus 2n. And the larger case would of course be n squared plus 1 all over n squared plus 2n. Because this function oscillates between -1 and 1. So then what we can do, we could bring back the n plus 2, and we want to have a 1 in front, so let's add plus 2n, subtract 2n minus 1. So if I have this on the bottom, and then let's do this. Plus 2n minus 2n plus 1. And of course, n plus 2. So then this simplifies to 1 plus -2n minus 1 all over n squared plus 2n. N plus 2. And we do the same thing here. Now we put this over 1. So we just put this to the bottom, and then we multiply by the inverse. I'll do it in this whole step. in this case would be negative. We do n squared converges to e, as we'll see later. Let's just do the left limit. We do the same thing with the right, so it would be just excessive to do. We multiply by the inverse. And then of course we have n plus 2 there. This goes to e, this whole thing. Or without this, so then we have 2n minus 1 times n plus 2 all over n squared plus 2n, and e is the power of this. Let's just take the highest power, 2n squared. So this would be 2n squared all over n squared. So this goes to e squared. Infinity. Now let's look at this little problem. It's telling us to prove that there is only one solution. And we have to use derivatives. So first let's plug in 0 to just see where an easy point of this function. We look around here and we plug in 0. 0 plus sine of 0, that's 0 minus 8. So we know that at 0 it's minus 8. Okay, now let's take the derivative. So this would be equal to 1 plus 2 sine of x over 3 times the derivative of this inside times the derivative of the inside. So times 1/3 and 0. Let's find any critical points, since we know that when the derivative is equal to 0, there's either a maximum or a minimum. Let's find when it equals 0. 2 sine take this there, multiply it, and negative 3. Alright, and then we realize that this looks somewhat familiar, and this is the identity that sine of 2 theta is equal to 2 sine theta cos theta. So let's go. Whoop. And now, when is this equation ever true? It is never true for any of x. Therefore, we do not have any points of this function where it is equal to 0. So it's never equal to 0. The derivative. So it never changes from positive to negative or negative to positive. So now let's observe the general behavior of the function, okay? So let's see whether it's always positive or always negative, or whether it's just flat. So let's plug it in here. Let's choose a random point. Let's find the derivative at 0. 2 sine, okay. This obviously evaluates to 1. So you see that the derivative at 0 is 1. So we can assume that the function goes like this, and we don't care what happens to the rest. All we care about is that it's always positive and it never crosses over itself, since it's a function. So it only has the opportunity to cross the x-axis and become 0 right here once. So therefore we just prove that there is only one solution.